Okay, good morning, everyone. Let's jump right away into our example for load line analysis of a common emitter amplifier. Okay, so we stopped here where we learned about operating modes and determination of operating modes. You have two topics remaining. One is the common emitter amplifier, and the other one after that is a fixed bias voltage divider fixed bias amplifier. So, transistor, when it was first invented, right, they proved that they could take an incoming signal and amplify it. Okay, so the primary application for a transistor is always as an amplifier. You take an incoming signal and you amplify it. Amplifying meaning making it bigger, in simple terms. The most common mode of operation is the common emitter, where the emitter terminal that you see right here is common to both the input as well as the output. This is the input side. This is the output side. So typically when you encounter circuits, you would always see something like this. Transistors with the base or the input on the left side and the output on the right side. Okay. Now, obviously, depending on how complicated the circuit is, that was changed, but this is pretty much the standard configuration and circuit diagrams that you would see. Here on both sides, the input and the output, first we apply a DC bias. So DC bias, again, as a reminder, is nothing but setting the operating point of a transistor. Okay, setting the operating point of a transistor. So we learned about the operating modes, right? If you connect the first junction, emitter base junction, either forward bias or reverse bias, and you have the second junction, the collector and base junction, and you can connect that as reverse bias or forward bias. So the biasing itself is basically preparing the transistor to say, okay, I want you to operate at this particular point. Okay, that's what DC biasing does. So the transistor is ready, and then the second part is, of course, the AC signal. So what you see in this image, what you see in this figure right here is the DC bias provided by VBB and VCC. Okay. So VCC is applied on the collector side, and VBB is applied on the base side, hence the names. Okay. But that notation could be anything, doesn't really matter. Just for simplicity's sake, we use VBB and VCC. So those are the DC power supplies. Those are the DC voltages that are applied to the transistor so that the transistor is prepared to take an incoming AC signal and amplify it. Okay. So as I said, this is a common emitter amplifier. It requires two power supplies, one for the input side, the other one for the output side. And common emitter or common base or common collector, again, as a reminder, simply states which terminal of the transistor is common to both the input and the output. So that's VBB and VCC. And then here, you see V in of T. That is the AC signal that we wish to amplify. Okay, V in of T. Again, remember from chapter 5 of 201, as a function of time typically indicates a time varying voltage, meaning an AC signal, an AC voltage or AC current. So if it's V of T or I of T, it's a time varying voltage or a time varying current. In this case, it's the AC signal that we wish to amplify. And then, of course, we are provided with the the characteristic curves for the input side and for the output side. On the input side, it's the base. On the output side, it's the collector. So it's the IV characteristic, meaning current as a function of the voltage. Voltage is on the x-axis, current is on the y-axis. So going forward, if you have a common emitter amplifier, common emitter circuit, it will always be on the input side as IB, base current, versus the base emitter voltage, VBE. And on the output side, it would be collector current, IC, as a function of the collector voltage, which is VCE. Input side, of course, it's forward bias, and so it is like a diode, forward bias diode curve. On the output side, it's almost a flat line. So you remember the transport model that that we showed or that we discussed. You have electrons crossing through the base junction. You have a lot of charge carriers crossing over the junction, and so you have pretty much heavy constant flow, and that's why you have this flat line for every single input voltage. Now, the reason we have a set of curves is because of the input current. So the input current is IB, and the set of curves shows you value for IC for every value of IB. Okay, for every value of IB. IB for 10, 20, 30, 40, 50 microamps, and so on and so forth. The reason we have a set of curves is because of the time varying waveform applied at the input. Okay, you have a DC voltage applied, so your transistor is fixed in position, so you're fixing the operating point of the transistor. Okay, you're fixing the operating point of the transistor, and we'll see that in the next few slides. Once you fix the operating point, when you apply an AC signal, now that operating point is going to move according to the value of that applied input signal. Okay, so think about that. You have a DC voltage that is applied. If you don't apply any input, you will obtain some output because of the applied DC voltages. But when you apply an AC input to it, that component is now added on to the DC. And so the voltage at the output and the current at the output, IC and VCE, will move correspondingly to the input applied current. All right, let's take a pause. Let me know if you have any questions about anything so far. Any questions? So I'm just noting down what I just talked about. Input side and collector IC versus VCE. So if you're following this, then can we determine what the beta of the transistor is based on the data that is given to us? Is a current amplification factor given by IC over IB. What is the value? Take any set. IB values are given 10, 20, 30, 40, 50 microamps. What is the corresponding value of IC? That's how you would read the spec sheet. For 10 microamps of IB, you have 1 milliamp of IC, factor of 100. For 20, it is 2, 30, it is 3, and so on and so forth. So this would be 1 milliamp divided by 10 microamps. So that would be 100. Because it is a ratio of currents, it is dimensionless, it doesn't have any units. So the beta value for this specific transistor is 100. Yes, 100. So far, so good. Okay, let's apply our analysis techniques and see what we obtain. So we'll split the circuit in two parts. Okay, we have, let me use the red. So we have the input side and we have the output side, right? This is the input, this is the output side. So anytime you perform an analysis, especially for BJT or an FET, for a circuit like this, you always want to divide it into two parts or multiple parts if you wish. I always think of it in those terms, input versus output. What is happening at the input side? What is happening at the output side? So let's first handle the input side. What analysis techniques can you think of? There's only three laws that we use: Ohm's law, KVL, KCL. Entire 201 course is just based on three equations. So which one do you think applies over there? KVL. We can sum up the voltages around that loop. If we wanted to, we could do KCL also, but now we have the voltages because we would know the applied voltages, we would know the applied signal, we would know the resistor value. The only unknown is VBE. So again, nonlinear elements, amplifier circuit, but circuit analysis techniques are still the same. They don't change. Okay, so we apply KVL on the input side. We see there are four voltages. Let's start from the bottom left corner. So we have this loop where we have V in of t. We have the voltage across RB. I will note it as VRB, base resistor. And then we have VBE. And then finally we have VBB. And they should sum up to 0. And again, if you have a preferred method that you're used to for applying KVL, feel free to use that. You do not have to use what I do. Okay, I typically just sum up all the voltages on the left side of the equation and I say everything is equal to 0. So then I have to do plus minus accordingly. So in here, I have minus V in. And because the current's going from left to right, I would have plus VRB plus VBE minus VBB equals to 0. Simple standard KVL. Okay. Minus V in minus VBB plus VRB plus VBE equals to 0. The same rules apply. We don't know what mode the transistor is in. So VBE could be positive, could be negative. We don't know. But if you're saying VBE, it means you're measuring the voltage at the base with the emitter as your reference, meaning the emitter should be minus and base should be plus. If it's VEB, you're measuring voltage at emitter with respect to your base. So then your base would be minus and emitter would be plus, which would be the case if it was a PNP transistor. Okay. All right. So far, so good. Any questions? Okay, so on the input side, we have our equation. Then we just solve that equation. Now, VRB has a current going from left to right into the base, which is IB. And so I can write V in of t plus VBB is equal to IBRB, Ohm's law, plus VBE. Out of these, this is known, and this is known. Okay, we know those three. The only things we don't know are the base current and the emitter base voltage. And we would use this equation to plot this load line. So we do the same thing we did earlier for the diodes. We plug in VBE equal to 0. If VB equals 0, then IB is equal to VBB plus Vin divided by RB. At one coordinate point when VBE is equal to 0, meaning right here, then your IB value is max, VBB plus Vin divided by RB. Make sense? Okay. The same thing happens when you have IB equals to 0, and then your VBE is equal to the input voltages, VBB plus Vin of t, Vin of t, which is right here. Take those 2 points, join them together, and you obtain the load line. And the interception point of the load line gives you the operating point right here. The intersection point is the operating point or the Q point, the quiescent point of the amplifier, the operating point of the amplifier. This is where we are biasing our circuit. If we don't apply any input voltage, if Vin is equal to 0, it's only DC voltages that have been applied, then of course it's simply VBB or RB, and here it's simply VBB. If Vin is equal to 0, right? So you can find the Q point or the operating point of this amplifier circuit without the AC signal. Meaning no input applied. Then it is similar to the diode the load line analysis. Okay. Any questions? Yes. You're asking about, let's see, if Vin of t is 0, we are getting rid of VBE. Which equation? This one or this one? Or both of them? No. I'm just saying that we applied the, so I think I see what you're asking. If Vin is 0, then do we apply it to this equation up here? It still works out to be the same, right? If Vin of t is 0, then this term is gone. The rest of it is still the same. Then this would go to 0, this would go to 0, and we just get IB is VBB over RB, and VBE is equal to VBB. So when Vin of t is 0 is basically, we are saying we have just applied the DC voltages, no AC input yet. We're just looking at where the transistor is with relation to our DC voltages. That's all. because we have biased it. We just want it to be in the center of the active region. And at the end, you will see in the graphical solution, I will show how and what happens when the signal is much larger. The input signal is larger than what happens when the Q point shifts to the far end of the load line. Okay. Okay, so that was the input side. Let's look at the output. Okay, it's the output. Output is also straightforward. We apply KVL. We have three voltages: VCE, the drop across RC, and then VCC. Okay, so three voltages. Let's wipe that out. And we apply KVL. Once we apply KVL, you can see I have VCE, and I will call this VRC, the voltage across the collector resistor RC, and then VCC summing up to 0. Once I place the signs, I would have, call this plus minus. I would have minus VCE minus VRC plus VCC equals to 0. VRC from Ohm's law, I can write as the voltage drop due to the current IC. So it'll be ICRC. And so therefore I can write VCC is VCE plus VRC. Instead of VRC, let me write it as ICRC. To find the two coordinates, I would substitute. If IC is equal to 0, then I obtain VCE as equal to VCC. And if VCE is equal to 0, then IC is equal to VCC over RC, max drop. Same thing that we saw in the diode, same thing we saw on the input side, same equations. That's the load line. This is the standard way to determine the load line. You want 2 points, you plug in 0 for the X and the Y axis, and you find out the coordinates for the other axes. And then you get this load line. All right, let's take a pause. Let me know if you have any questions about the analysis technique so far. Any questions from anyone? No questions? Okay. All right, then let's see how we can use this, or how we can show that this is amplifying. Okay. So let's say, so this is my output, obviously. I'm interested in the output. How do we combine both the graphs together? Well, this is how. Let's say I apply a signal. To make it easier, let's just do between 30 and 10. Okay, 30 and 10. So let's do it this way. And typically these curves that you see in the transistor are pretty linear, in the sense that if this is 10 microamps, then maybe for 5 microamps, the line would be here, 25, 15 over here, 25 would be here, and so on and so forth, typically. Okay, so let's say I apply an input signal that looks like this. Yeah. Let me give myself more space on the left side. Okay. Okay. And let's see, this is 10 to 30. So about 10 in this direction and 10 in the positive direction. Okay. Actually, BCE, IB max. I'm drawing the wrong one. Hold on. Do the output first. Okay. IB and VBE, that's the input. On the output, we have VCC and IC, and these are the set of curves for IB. So let's say I'm applying an input signal going from, let's see, IB min, IB max, about 2030. Okay, so on here and here. So IB varies from 10 microamps to 30 microamps. Okay, and we look at an example after this. Right now, I just want to show the amp, how we can actually use this as an amplifier. Okay, so let's say IB varies from 10 to 30 microamps due to an applied V-in signal. So let's say it's something like this. So if we fix our operating point here, then the input signal that is being applied, the input signal is actually moving the operating point above and below the standard DC biased operating point. Okay. So if you're applying an input signal, the input signal is going to move the operating point above and below the DC biased operating point. Okay. So you apply DC bias, you obtain an operating point, then this operating point will move up and down the load line in response to V-in. Because V-in is being combined with VBB at the input side. Remember this equation that we just had a question? If V-in is equal to 0, then the operating point is fixed in the middle, or depending on the values, it might be somewhere above or below the middle. But then when you apply V-in, if you apply V-in, what happens? Your operating point is shifting up this way, right? Your IB increases. Your IB increases, meaning it's moving towards the left. It's moving up the load line. When V-in decreases, meaning it's going negative, the AC signal goes negative below 0, then it moves in this direction. Correspondingly, on the output side, if IB is increasing, then you're moving in this direction. If IB is decreasing, you're again moving in this direction. Does that make sense? Right? When V-in is 0, you are at either ends of the load line. Q point is fixed in the middle. When you apply V-in of T, depending on the value of V-in of T, the operating point of the amplifier circuit shifts. It moves up and down the load line depending on whether the V-in is positive or negative. And when it moves, this is the most important thing. Remember, I talked about how the DC voltage takes on the shape of the AC input signal. And that's what it is doing. The Q point moves, the Q point on the load line moves in response to V-in. At the output, we have collector voltage. That collector voltage is coming from VCC, the DC applied voltage. So that voltage moves in response to Vin of t. And that's how we get an amplified output. If you don't apply anything, it's just a flat line. It's just a flat line at the Q point. But when you apply even a small input, then the Q point shifts, and then the output voltage takes on the shape of the input signal. Does that make sense? Let's take a pause. Let me know if you have any questions. And I'll finish up this diagram. Anyone has questions? It's a little tricky concept to get our heads wrapped around the first time. This is the input signal. This is the output current. And then we'll see the output voltage. Excuse me. All right, any questions? Okay. So if this is the input current, this is the signal for like IB, right? So if IB moves, then correspondingly, this is IC. And IC would be about, let's say it's not given, but let's say 10 milliamps in both directions. Okay. But look at what happens to VCE. And this is very interesting. What happens to VCE, the value? As IB increases, what happens to VCE values? Let me ask that question. VCE is our output voltage. If IB increases, what happens to VCE? This is 0, standard Q point, right? So VCE is fixed at that point without any V in. So whatever that value is, let's say 5, 10 volts, doesn't really matter. But as IB or VBB increases, VCE is moving up the load line. If it moves up the load line, it's actually decreasing. It decreases. If this goes up, VCE goes down. As IB or the input increases, VCE decreases. It still follows the exact same shape. If it's a square wave, it will output a square wave. It's a triangular wave, it will output a triangular wave. If it's a sine wave, you will get a sine wave, but it's correspondingly opposite. So what can we say about this waveform? If you give a small input, let's write this down first, correspondingly decreases, then VCE increases. So if you apply a small sine wave at the input, you add the DC biasing voltage to it, and the result is an amplified output. But what is the amplified output? What is the relationship? EE201, V of t is Vm plus sine omega t plus theta, phase shift. So the waveform at the output is 180 degrees out of phase. It is inverted. this is inverted. All right, let's take a pause, think over that. Let me know if you have any questions before we move on to an example. Questions from anyone? Yes. How do we know which angle to draw the straight line? Are you talking about this load line or these? Oh, those just, this right now it's very simplistic representation. The actual could be any angle, right? Depending on the value of the VCC and depending on the scale we choose. So if VCC is lower, then our load line could be like this. If you wanted the load line to look exactly at 45 degrees, we would just change the scales of the X and Y axes, if that makes sense. And then this is the input signal. So the input signal, of course, depends on the choice, incoming signal. It could be small, it could be very large. And again, this is a very simplistic representation. We have 10, 20, 30, 40 microamps. In your life, it might be like, 1, 5, 10, 15, maybe in smaller divisions. Any other questions? Okay, let's look at an example then. So in this example, we are given the input characteristic curves and then the output characteristic curves. Okay. First, we'll tackle the input side, then we'll see how it translates to the output. The given parameters are that the VCC applied is 10 volts. The VBB is 1.6 volts. So I will write down given information. VCC is 10 volts, VBB is 1.6, RB is 40,000 or 40 kilo ohms, and RC is 2 kilo ohms. Okay, 2 kilo ohms. There's 4 quantities. We know the values for all of them. So if we didn't if we are not given the input, we could just say, okay, DC bias is here. We figure out what the Q point is, and Q point is somewhere in the middle of the active region. Okay. But this is a given information to us. We have an amplifier circuit. We're either asked to design it, we are asked to analyze it. But this doesn't matter what we're asked to do with it. The analysis proceeds in the same manner. We take the input side first, apply the equations, find the Q point, then we transfer that Q point information to the output. And at the output, then we need V in of T. Okay. So V in of T is given as 0.4 volts peak and 1 kilohertz sine wave. Okay, it's a sine wave. So if I was to write this and extract information, it will be 0.4 sine of 2000 pi t volts. 0.4 is the peak value. It's not the peak to peak value. Okay. So the output side is, of course, VCE. So we want to find VCE values. And we'll find all three of them. Minimum, maximum, and at the Q point. Okay, minimum, maximum at the Q point. Okay, shall we begin? Yes. Just the DC bias. Yes. So the question being asked is about Q point. Q point is basically, yes, the DC bias. So let's see. V in varies from plus 0.4 to minus 0.4. So I can say V in minimum would be minus 0.4 and V in maximum would be plus 0.4, right? One peak. It's a sinusoidal waveform. So the positive peak is plus 0.4 volts. The negative peak is minus 0.4 volts. Okay, plus 0.4, minus 0.4. Let's write out our KVL equations for the input side. Like KVL, and we don't need to do the derivation again. We can directly write down IB is VBB. Yeah, that comes up more like DB. VBB plus V in or RB. VBB is given to us. You plug in the values. 1.6 plus V in is plus 0.4 and then minus 0.4 and then 0. So the three values for V in would be minus 0.4, 0, and plus 0.4. So VBB plus V in gives me three values for IB as 1.6 plus 0.4 divided by 40,000. That gives me 2 divided by 40, half. So that's about 50 microamps. Then I have 1.6 minus 0.4 divided by 40,000 gives me 1.2 divided by 4, so 30 microamps. And then the Q point in the middle, 1.6 plus or minus 0 divided by 40,000. And that gives me 40 microamps. So you have the maximum, the minimum, and the zero values. 30, 40, and 50. And on the other side, we have VBE and VBE plus V in. 1.2, oh no, 0.6, 1.2, 1.6, and 2 volts. And that's how we get our three values for the X and Y axes. Okay. Make sense, right? You got three values. You're simply taking the equations we derived from the previous slide, simply adding the values for V in over there. We take the three values, 0, minimum, and a maximum. 0 is basically when the signal crosses the x-axis. V in goes to 0, means Q point is right in the middle. And so you have three lines right there. This is the load line for V in is equal to 0. That intersects right here at IB equals 25. IB equals 25. Okay. When IB equals 25, that's a Q point or the operating point. And then V in goes to plus 0.4. That's the maximum value. We obtain a load line with a current of 50 microamps. And when it goes minus in the negative direction, 30. Okay. So the Q point, the instantaneous Q point is shifting up and down that input characteristic. Now we'll transfer this to the output. But before I do that, any questions? Okay. All right. Let's go to the output side. On the output side, now we have our three values. Okay. Our job is to determine what is the output voltage. Output voltage is VCE, collected at the collector or measured at the collector. So our three inputs are basically what? We have IB minimum at 15, IB max at 35, and then of course Q point IBQ at 25. So 15, 25, and 35. So on the output side, we find the characteristic curve for those three values. So we got 15, 25, and 35. Again, we analyze the input side first. We obtain the three values for the input current. That input current is going into the transistor. At the output, we are going to see how it changes the collector current and how it changes the collector voltage. So we got three values for IB, 15, 25, and 35. If I was to plot my input here, it would look something like this. And obviously this is not to scale. Yeah, that's still not good. What is happening? I don't know. That's weird. I know, but I've never had that issue before. Maybe it's a new gesture or something. Anyway, so that's my input, right? My input is varying between these two lines, 15 to 35. That's my input. Remember, V in of T was the voltage given to us as 0.4. We took that input voltage, V in of T, and we determined what is the input current going into the transistor. Then we take that input current, we translate it, no, we apply it to the output characteristic, and now we determine what the output voltage and the output current is. Graphical solution, okay? That's how we are using the load line analysis. If we extend this right here on the y-axis, we'll see this. It's not quite visible. And obviously, as I stated earlier, this is not to scale, or at least not the same scale. This is in milliamps. So I obtain what? 0.5 milliamps, going all the way up to 3.5 milliamps. Again, kind of factor off, let's see, 35, 30. So factor of 100, beta is 100. But look at what is happening to VCE. When you extend the intersection points to VCE, you obtain VCE between 3 and 7 volts. 3 and 7 volts. Yes. Oh, this is the output voltage. I mean, output current. Up 1.5, sorry. 1.5. 1.5 milliamps to 3.5 milliamps. Okay, so if you were to, this, of course, your image is already a solved example, so the load line is already plotted for us. But if you were analyzing this by yourselves, let's say as a design engineer, you would take the spec sheet, you would have the manufacturer would provide you these curves. Okay, so you would have the set of curves from the manufacturer. Then, depending on your application, you would apply some resistors, you would apply a DC biasing voltage, and you would create a load line. So the first thing would be to plot the load lines for both the input and the output. Then for any specified input signal, AC input signal, you can determine the input current going into this transistor circuit. And from there, you apply it to the output characteristics, and you can obtain IC and VCE. So IB values, are from the input characteristic. Okay, input characteristic. And then when you translate it to the output characteristic, the intersection points, for IC and VCE. The intersection points give you the values for IC and VCE. So from here, we know IC has a range of 1.5 milliamps to 3.5 milliamps. Given value of IB was actually, let's write IB first and IC afterwards. So my input IB was 15 microamps to 35 microamps. Okay, 15 microamps to 35 microamps. My output current IC was 1.5 milliamps to 3.5 milliamps. And more importantly, voltage, output voltage VCE goes from 3 volts to 7 volts. My input voltage, if you compare V in of T varied from minus 0.4 volts to plus 0.4 volts. Output went from minus 0.4 to 3 volts and plus 0.4 to 7 volts. So my output is varying like this. Okay. This is 3 volts, 7 volts. And this is a graphical load line analysis. All right, questions? Let's take a break. It's 11:06. Let's take about 4 or 5 minute break. We'll begin again at 10:10 or 10:11. In the meantime, if anyone has questions, feel free to ask.